Welcome friends, welcome back to our channel Crystal Learning. So today we will see the subject heat and mass transfer. So this question came in a competitive exam. A student asked me, but I don't have the information about that exam. Okay, but it came in a competitive exam. So it is asking about NTU refers to the number of transfer unit passes required for effective heat transfer. Then B option, that is compactness of heat transfer unit. Then correct answer is C, the closeness of heat exchanger with its thermodynamic limit of operation. So we will see this term, what is thermodynamic limit of operation and this closeness of heat exchanger. So let's study, and let me make it clear that we won't go into the derivation part. We will just using the formula and the graph upon which this question will become clear. Okay, so this topic comes into that heat exchanger part, heat exchanger chapter. So there you can just see the derivation of and all heat exchanger. Okay, number of transfer units NTU. So heat transfer effectiveness is defined as actual heat transfer rate upon maximum possible heat transfer rate. So for maximum heat transfer possible rate, you have to be that delta T max, that is hot. H is for hot fluid, N is inlet condition, OUT is for outlet condition, and TC is for cold fluid and in. So we see for maximum heat transfer rate, this delta T has to be maximum, and therefore C, that is heat capacity rate, has to be minimum for that. Okay, so that this term become maximum. So maximum heat transfer rate. So there is a thermodynamic limit possible for maximum heat transfer rate. What will be that maximum possible heat transfer rate? That is C minimum, because hot fluid will be have some C, and C will be a cold fluid having some C. So in that too, whatever the minimum value will be there, you will put there here. And this condition, that is hot inlet minus T cold inlet. So this is the maximum transfer heat transfer rate. So effectiveness is defined by two ways, that is for hot fluid EH and for cold fluid. So for hot fluid it is MHCH TH inlet minus TH outlet divided by minimum. So heat transfer, this maximum rate case will be in both the cases will be same. Okay, just see this two definition, it will be same, but that it will depend upon the minimum value. What will be the minimum value of that cold liquid or hot fluid? So depending upon that, the formula will change. If suppose that hot fluid having minimum value of C, then this formula will become, you put C, then CH will be become C minimum. Okay, so this C minimum and this C minimum cut, and this term will come of temperature terms. Okay, and suppose that C is minimum, then it will be C minimum, and this C minimum and this C minimum cut out, and we will get in temperature term. So this is in some books, it is also this effectiveness is referred as temperature effectiveness. Okay, temperature effectiveness. And we see there is a maximum limit of this EH and EC depending upon the temperature condition. So it can't be an infinite, there is a limit of the value of EC and EH, up to what value it can reach depending upon this temperature values. Okay, so there is a condition. Okay, a limit is there, so it can be given by EH or EC. Okay, so effectiveness of parallel heat flow conditioner given from this equation, it can be derived. So in theory lecture we will see the derivation and all that, but here we assume that this is the effectiveness of the parallel flow condition. So in this term, that is U AS upon C minimum, is defined as NTU, number of transfer units. Okay, so if we see that here it is dependent on overall heat transfer coefficient U, heat transfer surface AS, and C minimum value. So for the specified values of U and C, if we make this U and C as constant, so we see that NTU value is depending upon surface area. So this statement can be said, that is larger value of NTU means larger the heat exchanger, because AS will be large. If NTU is large, and AS will be large, and the larger will be the heat exchanger. Okay. Then this C is defined as its capacity ratio, that is C minimum upon C maximum. So effectiveness is we see that it is a function of NTU and C. So for parallel flow, this term will reduce to e to the power minus N2 in terms of N2 and C. Similarly for counter flow also. Okay, N2 and C. So this graph, you might have seen this graph. So from this graph, we will draw the conclusion of that question. So here we see this graph is the C is value is 0, that is C minimum upon C maximum equal to 0. This value is 0.25, this value is 1. So here we see effectiveness value range from 0 to 1, okay, first point 0 to 1, and here we see that for C equal to 1, the maximum effectiveness range is around 50%, and that will only reach when NTU value is at infinite, means this value will cut this line at infinite. So this curve is asymptotic curve, or this value is known as asymptote. Okay, asymptote means if there is a limit given, so that graph will cut at infinite time or infinite distance, means you increase this NT value up to infinity, at infinite this both curves, means this 50% line and this curve will meet. Okay, so asymptote means it is close to that point or limit but not actually touching, and it will touch actually at infinite. So this is the meaning. So here we see at low values of NTU, we see effectiveness of all the curve is low. Okay, all the effectiveness values are low. But as we increase NTU value, so this effectiveness is increasing and reaching a constant value. Okay, just see this constant value; it is reaching this constant value, and after that, if you increase the size of that heat exchanger, you won't get better effectiveness. So it defines that what will be the that maximum size of the heat exchanger where you will get the maximum effectiveness. Above that, if you are increasing the size of the heat exchanger, there is no improvement in the effectiveness value. Okay, so these things can be drawn from this graph. So let's read out some sentences. Okay, so from figure 1, the temperature effectiveness curve for different values of heat capacity ratio tend to converge and approach a constant values as NTUs increase. So all these values are converging and reaching a constant value, okay, for different C's. And why it is happening? This is because in each case there is a maximum limiting value of EH and EC. There is a maximum corresponding to the asymptotic values of effectiveness which could be achieved in exchanger of infinite size. So where this asymptotic values is reaching at infinite, when that infinite size means NTU is getting infinite value, then only that will touch. So from this graph it is saying those points. Okay. So these asymptotic values are thermodynamic limits which are fixed by relative magnitude of heat capacity rate. Effectiveness, we have seen that it is depending upon what, that is heat capacity rate, and what will be the inlet temperature. On these values it will depend, and are independent of heat transfer mechanism involved, that is conduction, convection. It won't depend on that, it will depend simply on capacity rate. We have seen that that maximum heat exchanger transfer rate depends upon capacity rate and inlet temperatures. Okay, so these points are we have seen here. So let's read out some more points. What is asymptote? Asymptote means approaching a value or a curve closely, or some sort of limit is taken. Okay, some limit is there. We have approached that value closely. A line or curve that approaches a curve arbitrarily closes their point of touch tends towards infinite. So this is the mean of asymptote. So it can be seen that at low NTU, exchanger effectiveness is generally low. We have seen in the graph. With increasing the value of NTU, the exchanger effectiveness generally increase. Effectiveness value is increasing, and in limit it approaches the maximum asymptotic value, that is maximum effectiveness irrespective of the size. So here see, when you are increasing this NTU value, so this effectiveness is also reaching its asymptotic values. Means asymptotic values means maximum limiting condition of this effectiveness, and asymptote means this graph will touch at infinite point. So there is a condition, means after that if you increase the size there is no improvement of this effectiveness value. So that was the meaning of that sentence. Okay, so this maximum effectiveness of, or NTU asymptotically approaches infinity. We see NTU is reaching to infinite distance, that is large values of NTU. Then the closer the heat exchanger approaches its thermodynamic limit. So as NTU is increasing, we see that effectiveness is also approaching its maximum limit or maximum effectiveness, whatever it can touch. So we can say that values of NTU refers to the closeness of heat exchanger with its thermodynamic limit of operation. Suppose, for example, we have taken this graph. this one of C equal to 1. So we know that it is 50% maximum efficient. So if suppose our value is given 0.5 NTU, so we see how much close it is to that maximum value, this much close. Okay. So if it is increased to 1, we see this much close. If it increased to 2, we see this much close. So it is indicating the closeness of the effectiveness values up to the thermodynamic limit. So we are comparing our that this is the thermodynamic limit of this exchanger. So how much close it is with that thermodynamic limit of that heat exchanger. So that is the answer of this question. So now I believe that's all the meaning of this question is clear. That is NTU refers to the closeness of this heat exchanger with its thermodynamic limit of operation. What will be the maximum effectiveness? This thermodynamic limit means maximum effectiveness of heat transfer, okay, of that heat exchanger. What is the this thermodynamic limit of operation means maximum effectiveness value of that heat exchanger. So NTU value will refer that how much it is close with that maximum limit. Okay, so I hope you enjoyed that this lecture, and the concept of NTU and this thermodynamic limit of operation is clear now. There is no confusion. So we will meet in the next lecture with a new concept. Till then, have a nice day.